Hello everyone, my name is Chen. I come from North Minzu University, Ningchuan, China. Now, I'll present our paper, Feature Attention Module for Context-Aware Image-to-Image Translation. Image translation is a long-standing and challenging task in computer vision, and lots of problems can be viewed as the image translation, such as super resolution, colorization, inpainting, and style transfer. An Indian network for image translation should be context-aware, which should not only have the ability of finding what the differences between the source domain and the target domain are, but also have the ability of judging which parts should be affected and which parts should be returned during translation process according to the context of translation tasks. Look at these images from this slide. When the image in summer is translated into winter, the girl in the source image should remain unchanged, while the grassland must be translated from green to gray. When we aim to translate house to zebra, the house in the source image should be translated to zebra, while the background should be retained. However, current unsupervised one-to-one image translation techniques fail to focus the translation on individual objects. To solve this problem, in this work, we propose a generic and flexible feature attention module which can be added into existing unsupervised one-to-one backbone image translation architectures and produces context-aware translation results. This is the architecture of a feature attention module. Supposing that the input feature map is X. Step 1. Constructing 3 embedding feature spaces through cross-channel iteration and information integration based on point-wise convolutions. Step 2. Calculating the most simple feature as the global feature at each plane of feature maps in the first 2 feature spaces. The global features include C average features and C silent features by global average pooling and maximum pooling. Step 3. Calculating the feature correlation matrix F, whose element Fig reflects the correlation between the I's average feature and the J's silent feature. Here, each feature map can be regarded as a feature specific response, and different feature responses are also associated with each other. Consequently, the resulting covariance matrix F has clear physical meaning. For instance, its I's row indicates statistical dependency of channel I with all channels. By exploiting the interdependencies between channel maps, we could emphasize interdependent feature maps and improve the feature representation of long-range space dependencies. Step 4. Getting a non-local feature map Y by multiplying the feature correlation matrix F and the last feature, which captures the response of every position to global features of this image by weighted summation C features of this position with the weights as the correlation coefficient between features. Step 5. The non-local feature map Y is multiplied by a parameter lambda and added to the original feature X to obtain the context-aware enhanced feature OX. In order to illustrate its basic process of how FA modules enable context-aware image translation, we visualize the refined features in the third and first layers of this generator in UGAN using GradCam. It means that the regions of same colors in GradCam correspond to same concepts. Consequently, it can be shown that after adding FA modules, the regions of same objects can be distinguished in translation process, and the object size that the network can distinguish is getting larger from the third layer to the first layer. This resulting indicates that FA module can identify objects from feature maps based on the feature similarities at different scales. Therefore, FA module can be armed with image-to-image translation network to enable a context-aware translation. Specifically, we designed three kinds of FA module aiding methods for cyclogram, duogram, and unit, respectively, according to their image translation frameworks. The details are shown as this figure. As A shows, in a unit-like network, the deeper the layer is, the larger the local respective field is. Considering that our FA module is designed to capture the points or the regions of same objects, the feature maps in deeper layer may be too abstract to help capturing the same objects. Therefore, we add FA modules to each output of the first four convolution layers of a unit-like network. As B and C show, in the ResNet-like networks, the feature maps of deep layers contain both abstract and fine-grained feature information of input image by the residue connection. Therefore, the FA modules are added to the last res block in the generator of cyclogram and similarly to the last res blocks in the encoder and the decoder of unit. We first show our qualitative results. We use duogram, cyclogram, and units as the baselines in view of their state-of-the-art performance and high efficiency. Considering that SAGAN is designed for class conditional image generation tasks and cannot be directly used for image-to-image translation, we add the self-attention module into above baseline models and compare with them. In addition, we also compare with the attention-guided image-to-image translation method because it achieves outstanding translation performance based on attention mechanisms. We conduct experiments on 4 public datasets: winter to summer, apple to orange, house to zebra, and day to night. Because these datasets contain natural scenery, animals, and fruits, and have completely background, the context-aware image translation experiments are very challenging. Observing the experimental results on various datasets, we can see that our method obtains a better visual effect compared with the state-of-the-art methods. For example, in the winter to summer translation tasks, all other methods mistake the bird and the boy as part of target regions and transform them into another undesirable color more or less. In contrast, by adding FA modules into duogram, cyclogram, and units, all methods transform relevant image regions and ignore other irrelevant regions. Similar phenomena existing in other dataset translation. Among the state-of-the-art method, the method attention-guided has the best translation ability by introducing unsupervised attention mechanisms. Compared with this method, our method demonstrates the following 3 advantages. The first one, the domain, irrelevant regions or backgrounds of output images are more consistent with the original image. The second one, the domain-relevant regions are translated closer to the context of target domain. More details are captured and translated, such as the apples hidden behind leaves in this image. We show more comparison results on the winter to summer dataset. It can be found that if the input image don't contain any target regions distinguishing summer from winter scenery, the added FA modules don't change any part of the images. In contrast, all other methods do change parts of the irrelevant regions more or less. The quantitative comparison results with recent state-of-the-art methods on various datasets are shown in this table. It can be observed that the first one, for every baseline, the new network armed with FA modules significantly outperforms original one, and the one armed with SA modules on almost all datasets. The second one, further comparing our method with the method of attention-guided cyclogram at FA and units at FA have evident advantages over it. The last one, although the performance of FID is not as good as KID by employing FA modules, its overall traits are same as KID. In order to further assess the context-aware translation ability, for instance, the ability of objects transformation and background preservation, two-element matrix SSRM, PSNR between generated image background and original image background are introduced. It's obvious that cyclogram and FA is superior to cyclogram for house to zebra and zebra to house in both PSNR and SSRM, which indicates that the proposed FA module makes translation network focus on domain-relevant regions, and thus achieves context-aware translation results. We also use our FA to multimodal translation. We select the state-of-the-art multimodal translation networks, MUnit and DRITE, as baselines. It can be observed that MUnit and DRITE can produce multimodal results, though they fail to find which object should be translated. When adding our FA modules into these translation networks, the apples or the oranges are also translated to multiple different appearances. By observing the KID and FID compared with original multimodal translation networks, adding FA modules reaches much lower values, which also validates the visualization results. Both self-attention and feature attention are configurable for exciting image-to-image translation networks, which will result in additional computational costs. Supposing the image size is n and the number of channels is c, the SA modules time complexity and space complexity are O(n) square, while the FA modules times complexity is O(n) and the space complexity is O(1). For instance, the proposed FA modules are insensitive to the growth of image resolution. The experimental results shown in this table on the dataset day to night prove this conclusion. That's all. Thank you.